Today's webinar is on TotalCAE HPC Technology Choices for Accelerating Abaqus. What we're going to cover today is a little bit about TotalCAE if you don't know who we are. The technology choices we use to speed up Abaqus, some new features of GPUs for Abaqus Explicit, how do you choose between different CPUs, between explicit and standard, Abaqus network and disk recommendations for explicit and standard, a little bit about the Abaqus job layout engine and how that works, and how you can kind of perform what it does when it does not engage, and a little bit about job stacking on modern processors, and a quick case study at the end. So if you do not know about TotalCAE, what we do is we sell turnkey clusters that are managed by us in your data center that reduces simulation time by up to 80%. It's like HPC as a service. We wheel the cluster in. It's pre-optimized with all your applications, and then we run it and manage it, including all your apps, the operating system, everything up from the time you submit the job all the way to the time you get it back. So we eliminate IT headaches that people often have with clusters, make them highly reliable, and we're an expert in a wide range of apps, AI workflows, optimization workflows, and tools, so that your engineering department has a dedicated group that's an expert in this field to help you meet your deadlines and accelerate your workloads. So we do the same thing if it's in the cloud. We will manage everything in your cloud subscription, the same kind of environment, just happening to sit on cloud hardware instead of a real cluster. We'll update all your apps, like I said, and we include an easy-to-use portal that has a lot of tight integrations with the applications that makes it easy to submit, manage, monitor, get analytics, easy as 1, 2, 3. Upload the model, pick the kind of hardware that's been pre-curated for your app, and push the button. We support hundreds of apps, all the major cloud vendors, and we sell and support our own clusters, and we can help you design and manage a cluster if you have an enterprise requirement to use a specific cluster vendor. We're familiar with all the major hardware suppliers and can help you validate and optimize for that, and then we can manage it for you. Again, we do everything from the time you push the button till the time you get the result. Everything in between is TotalCAE's responsibility. If anything goes wrong, you just call us, and within 1 hour, one of our IT experts is going to help you figure out why your model's not working, what's going wrong. Is it the model? Is it the app? Is it the scheduler, the MPI, the Linux, the hardware? There's a lot of moving parts in HPC clusters that make them difficult to manage and support, but that is all we do every day for hundreds of clients, so we can help you get and keep your deadlines with TotalCAE. So now let's talk about the primary focus of this call is how do we put together clusters, systems to accelerate performance. And it always comes down to having the right CPUs, GPUs, network, memory, and disk. Even with all those things correct, you still have to have it all configured correctly and know the right options to take advantage of all this. And this is what this talk is going to dive into a little bit. Now I'm going to skip to the more exciting part, GPUs. Now, at the time of this recording, Abaqus 2026 now has Abaqus GPU support with explicit. It's been in standard for a while, but now you can actually run GPUs with explicit. And it works with even single precision, more affordable cards that are often AI related, like the L40S and the RTX Pro 6000. Even though those are single precision, double precision can be performed on them, and the performance is actually quite good, and we're going to show that here in a second. Now, there are some limitations, which you can check the documentation on, but it does work very effectively. Now, first model is going to show the best case scenario where you don't have a lot of contact. This E11 model then runs mostly on the GPU equations. We have our baseline model. By adding one GPU, I'm able to speed it up 1.19, and 2 GPUs almost double the speed up over just a CPU only run. So that's pretty nice. This E11 model has about 10 million degrees of freedom and 3 million elements. Now, if you have a lot of contact, like this crash model here, this E13 model, the speed-ups aren't quite as dramatic because that is still being performed some on the CPU, so some algorithms are on the GPU, some on the CPU. In this case, though, we still get a 1.32x speed-up by just adding one GPU to the baseline CPU-only model. So your mileage will vary just depending on how your model is, just like it has with Abaqus standard in the past. Same holds true for Abaqus explicit. But an exciting innovation here that the team put together on the latest version of Abaqus. Now, if you're interested in GPU computing, we do have an entire series on GPUs. What ones are single precision and double precision, and what do you need to know? Too much for this webinar. So see our GPU series or ask for our ebook on GPU computing if you're interested in GPU compute and how it can help you on different types of applications. Now back with Abaqus, again, CPUs are a core piece of solving any kind of application. And so picking the right CPU for the type of the application you're doing is kind of important. But a key takeaway is, for the most part, always running on the latest hardware is going to give you a better performance. So in this case, we're going to take E13, and this is very much a memory bandwidth bound problem, and newer processors have better memory bandwidth. And so we are now at looking between just one, basically between the previous generation, the latest generation Intel processors, we're getting a speed up of 21%. Same token cost. So exactly the same cores, 64 cores, you're getting a speed up of 21%. Nice bump up with for the exact same token cost. Now, explicit is memory bandwidth bound. What is memory bandwidth? It's kind of like how fast can the CPU fetch data from memory. So having big caches, having a fast memory, there's many things that go into memory bandwidth. But I just wanted to show an example of just taking one processor here. I'm running all the cores, and I get a specific runtime. If I run half the cores on the node, I effectively double my memory bandwidth per core because each core has more L3 cache dedicated to it, more of a dedicated pipe into the from the CPU to the memory. And you can see by just running the exact same number of cores, but giving it double the memory bandwidth by running on two machines, I am able to get a 30% improvement in this explicit model because it is memory bandwidth sensitive. So the takeaway is when you're looking at new configurations, if you're running explicit, you want to favor memory bandwidth configurations that give you the most memory bandwidth will generally result in more performance, more than just throwing a faster clock at it, for example. Similarly, on AMD, if you go back a couple generations and then you compare it to the 5th gen Intel, the memory bandwidth on the AMD is steadily improved, bigger caches, and all the same story there too. We got a 2x improvement between those generations, between AMD 3rd gen and 5th gen on the same 192 cores, same token cost, twice the improvement in performance. And I was able to use half the nodes. The latest generation had 192 cores per node instead of the 96 cores per node that I had run on this Milan. Now, for explicit, it's a little bit different. There, it's not memory bandwidth sensitive as much as it is clock speed sensitive. So showing here, going on a previous generation processor running at 2.3 gigahertz baseline, by running on 32 cores of that and keeping the token cost the same, on the latest generation running at 3.6 gigahertz, I was able to get a big speed up from 4,424 seconds to 2,927 seconds. Same token cost, primarily driven by clock rate. Now, if I would have taken a latest generation Intel Xeon 6 and ran at like 2 gigahertz, wouldn't probably get that big bump, so it's not just always going to the latest processor, but making sure you have the right processor for what you're running to get the performance that you're looking for. Now, in terms of networking, generally with explicit, if you're running large core count machines that you're going to do multiple of them in a single job, you're going to want to have InfiniBand. InfiniBand is a low latency network that moves data between machines under a microsecond, where an Ethernet might be in the millisecond. So multiple orders of magnitude faster, and that means that as you add nodes to your job, it speeds up. It doesn't slow down from having too much communication overhead. If you run just single node jobs, you don't need InfiniBand. But all TotalCAE clusters come with InfiniBand, so it's a very simple, you don't have to worry about it, but just be aware if you're doing something on your own, do you need InfiniBand or not? Kind of depends on how big of jobs you run. Do you use more than one node or not per job? If you're running Abaqus standard, you might want to have NVMe SSDs for Scratch. It helps speed up calculations that get done inside of the local Scratch. In the TotalCAE portal, you can just click on a button to automatically move all your data onto a local high-speed SSD and run it, crunch it there, and move the data back. Or you could use a parallel file system if you have a high-end cluster with the parallel file system for Abaqus standard. Also help keep your performance optimized from a disk perspective. Now you can have all the best hardware in the world and still misconfigure it and run poorly. So this is about a little bit about what can you do outside of hardware. One big thing you can do is update to the latest Abaqus releases. Each Abaqus release updates the MPI, which is like a key technology that helps you take advantage of the latest innovations and interconnects. It also adds new capability, like we talked about, different kinds of GPU capability on each release, being able to have more optimized compilations for the different chips. So, if you really want the best performance, generally going to the later releases is going to unlock more of the hardware that you've paid for to get better performance. Also, like one of the innovations in one of the releases was Abaqus introduced a job layout engine called the JLE. And you can think of it as before, you might have to think a lot more about the hardware, like how many processors do I have? How am I going to lay out what's called those MPI, message passing interface ranks, and the threads that they use. And what they came up with was kind of a heuristic to help. And then what it does is it looks at, host you're on, the cores per host, and then based on the memory per core, it tries to optimize the number of MPI ranks and threads per MPI rank for you to give you a better performance without you having to do any tuning or knowledge. And so this is kind of the rules of thumb that they have in the JLE. If you're using Abaqus standard with the direct solver, if you have more than 8 gigs per core, it has an algorithm and it says T is going to be the divisor of C closest to 10. If you have less than 8 gigs per core, it's going to pick a divisor of C closer to 20. AMG is going to have a C closer to 4. Now, Abaqus explicit, generally a JLE is always going to say 1 core per MPI rank. Now, JLE does not do any layout if you do not use all the cores on the node. If your machine has 192 cores and use 32, the JLE does not kick in because maybe they don't know what you're doing with those other cores. It doesn't know what optimal might be depending on what else you're doing. Now, you don't have to do anything to use the JLE. When you run, I'm showing an example here, you're going to see it say running job layout engine. You might have seen that not knowing what it was doing. Well, what it was doing is trying to optimize the MPI ranks and threads per rank in the background. So in this case, I ran a 192 core job on a 192 core machine at 2 CPU sockets, each with 96 cores, and at 3 terabytes of memory, so I had 16 gigs per core, which is quite high. And so this model then invoked the direct solver, and it chose a layout of 1 times 24 by 8, which means a node with 24 MPI ranks per socket, 12 MPI ranks per socket, 24 total MPI ranks with 8 threads per MPI task. That gives me 192 cores, and you can kind of see a visualization of top on the right-hand side on Linux showing those MPI ranks. Now, the threads you won't see in top, but you can push a button which would show you the CPUs and see that those are utilized. Now, what's kind of important to know is that if you don't use all of the cores, like I said, JLE is not engaged. So in this case, I have a 128 core machine and I'm running 32 cores of it. Well, if I only run 32 cores, the JLE is not invoked. So I kind of have to do what JLE does for me manually. So I am providing an Abaqus option called MP host split, and I'm telling it to do this optimization for me. And by doing that on the same hardware and the same token cost, I was able to get a 41% improvement, same hardware. Why wouldn't you just run 128 instead and let JLE do it? Well, it takes more tokens. In that case, maybe I don't want to run 128. So having some knowledge of what JLE does and that there's ways to do what JLE does manually, which is what we had to do in the olden days and old versions of Abaqus, then just that will give you more performance, same hardware, same everything. And today's modern CPUs are a bit more challenging for getting performance on in certain configurations. Now, what we do is we glue together small CPUs called chiplets. We glue them together to get to very high core count processors. So in this case, we have these 12 CCD configuration. There's a bunch of little cores, and then we kind of glue them all together to make these high core counts. And so I had talked before about how memory bandwidth was quite important. And so you can see each one of these chiplets has its own cache. And so if you're going to run, for example, a 12-core job, you may want to have each of those cores, each one of those MPI processes mapped to its own cache and have maximum memory bandwidth. So that's what this green line is representing. It said, if I'm going to run 12 cores, let me do one per each of these little chiplets. That gives each MPI rank that's running on that chiplet the maximum memory bandwidth to memory. I get the whole L3 cache to myself, and the whole path to memory is not shared with anybody else. Now, you have to sort of lay it out this way. It doesn't always guarantee to automatically do the optimal thing, but that is how you can get the highest performance, is by having some understanding of what you're running on. But it also helps explain why, when you do job stacking, you may see different performance degradation between explicit and standard. And the reason is, what is job stacking? Job stacking is saying, I have 128 cores. I'm running a 32-core job. Why can't I just put 4 jobs on there? I'm wasting all these cores by running 32. But you can see that certain core counts are more optimal than others. So in the optimal configuration of not stacking, I'm able to get this baseline performance. But as I run more explicit jobs, I'm not getting the I'm reducing the memory bandwidth available. It might not even be the optimal method when I'm stacking. And so I can see in this case a 39% performance degradation between 2 jobs. I'm running 2 jobs at the same time. Each job is 40% slower than if I would have ran one at a time. Now I'm getting more throughput perhaps, but just to see that I'm getting this performance degradation, people might say, well, why? Because in our TotalCAE portal, we let you just decide if you want to stack or not. Many people have to stack because they may not have enough hardware, but you're going to see a degradation because of getting worse memory bandwidth. As you add more cores, the memory bandwidth per core is not as good. Now with explicit, it's not memory bandwidth sensitive, and so we now see we get a lot better performance degradation, less degradation I should say, when we run 2 jobs at a time. We're only getting a 16% slowdown. It might be quite worth stacking a whole bunch of standard jobs on a single machine, because it is only 16% slower, but I'm getting double the throughput practically by running 2 at a time if I'm limited in hardware. Now, if you have unlimited hardware or have enough hardware, you of course should run 1 job dedicated per machine's best performance. But if you're in a situation, which many clients are, that they need to share too much of the hardware with others, and you want a job stack, you will see with standard less degradation than you would with explicit. Now, one thing is that many people say, this is all great, but I can't afford a cluster. Clusters are too expensive. But indeed, they are not for the rich and famous. You can definitely afford a cluster. If you have 5 or 6 engineers and a lot of tokens, you have quite an investment, and you can really optimize that investment for a very low cost. A very small HPC, kind of the minimalist size, has a management server with some storage. You usually have at least 2 nodes in a cluster. You can have different kinds of machines depending if it's explicit or standard, and then they're connected with InfiniBand and a management switch, and have a 4-year lifespan. So they come with a 4-year warranty. So something like this will start at like $1,400 per month. So if it's worth it to you for $1,400 a month to dramatically increase your throughput, get more performance per person, more performance per Abaqus token, this is within the budget of most customers. And if you have, if it's more than just yourself running, and you have a team, you're going to get your payback. You're also going to be able to do things that workflows you couldn't do before, like schedule around your Abaqus tokens, be able to keep those tokens busy 24 hours a day through job schedulers that are part of the system and that we help set up and integrate and manage for you. So clusters are affordable. Don't think they're just for the rich and famous. So one case study here where we came in is we had a customer, Divergent 3D. We won an award with them because they wanted to get up and running quickly with an HPC cluster. They had an IT team, but they're very busy, and they wanted to have somebody that just took care of the whole thing. The engineering department's here, just make them as happy as possible, as productive as they could be. So we wheeled in a TotalCAE cluster. We were able to get them up and running quickly with all their applications. The IT director was thrilled that the team was, totally happy. They could focus on their thing. Engineers were able to keep their deadlines. Were able to keep them happy, and they do really cool. Like their product helps design like these 3D printed supercars from Singer. Pretty cool. stuff. We won the HPC Wire 2023 Reader's Choice Award nomination here with Divergent for our work with HPC, helping facilitate this process. So TotalCAE is kind of an IT subscription. We win your business every month. You subscribe to us, and we include everything you need: hardware, application, installations, the portal, the scheduler, operating system. The only thing we don't do is we don't sell the Dassault licensing. You're going to work with Dassault or your reseller. We will install, manage, and upkeep your license, or we support managed DSLS as well. So we do all the IT aspects of that. And we run that all in your data center, or you could also do it and bring your own cloud. And so, yeah, if you're interested or wanting to get help, adopting HPC, or maybe you have HPC that's just not working well for you now, and you just want you want to have a rock solid, bulletproof, production ready cluster, contact us. We're going to help take care of everything. If you're interested in a deeper dive, we do have an HPC blueprint ebook on Abaqus that gives us a lot deeper dive of what we covered here, and more of our integrations and a demo of running Abaqus on TotalCAE, how easy it will be. Run just like they're used to. So just reach out to us at info@totalcae.com, and we look forward to seeing you on a future webinar.